So it's my honor to introduce our next speaker, Professor Eun-Ah Kim from Cornell. Today she's going to give the first of two lectures. Her second one will take place tomorrow. And today she's going to be talking about orbital geometric frustration in moiré systems. So would everybody please help me welcome Professor Kim?
Thank you for the introduction, and I'm really honored to be here. It's my first time visiting IAS, and I had no idea how beautiful and peaceful it is here, so I've been enjoying my first visit. So I want to talk about orbital geometric frustration in twisted bilayer graphene. Now, this is right after lunch, so if you're like me, it can be a little sleepy. Unlike the previous speaker, I am a theorist, and I understand many of you are experimentalists here. So I wanted to strategize so that you can get something out of this talk, and without demanding, that you follow through a lot of equations. So I try to minimize the number of equations, but there will be a lot of pictures. So you have to pay attention to the pictures. I'm really happy to talk about this physics because this is sort of very simple and beautiful, and at the same time really rich. And I'm hoping that you would get as excited about all this as I am. It wouldn't have been possible to learn as much as we've learned without the help of, or rather leadership of, my junior group members. Kevin Zhang was my graduate student. He just graduated. Dan Mao is a postdoc. Dan and Kevin have spearheaded most of development. We've had a pleasure of interacting with Yang Zhang and Liang Fu, and experimentalists at Ohio State University. Our collaboration with experimentalists just got published in Nature Physics this July, and we have new adventures that we are pursuing with Roderick. And here are references that will cover the two talks that I'll be giving today and tomorrow. If you are interested in knowing more details, here are the QR codes. You can take picture, and you can look up the papers later. All right, so fractionalization. We think about correlated systems, which has kinetic energy and interaction energy. Very well-established paradigm of thinking about fractionalization is that of fractional quantum Hall effect, where you first think about kinetic energy or free electron physics. You think about your electrons under magnetic field forming this flat Landau level, and then you ask what should happen if you fill it partially. Without interaction, you should have a gapless system because there are a lot of states that you can move around. Once you add interaction or project the interaction to the lowest Landau level, you can get fractional quantum Hall effect. And this is a well-established paradigm which has been very successful. But you can also ask, can I flip this narrative? Can I think about a degenerate state, extensive degenerate ground state, starting from strong interaction? So that would be a strong coupling limit or a classical limit. And you can have a situation where you have this very degenerate many-body spectrum. Now, this is not the first year, or rather your first quantum mechanics exercise. It's a little more involved, but you can be in such a situation. The advantage of thinking about such a scenario is that you might be able to have fractionalization right away. And you can then ask, can that fractionalization or rich physics that you discover, starting from strong correlation limit, can it survive with quantum fluctuation? Now, I didn't make this up. This is a well-pursued paradigm. Now, you might ask, how do I get this extensive degenerate ground state? The way to get the extensive degenerate ground state is a geometric frustration paradigm. So this is sort of a canonical example of discussing geometric frustration. If you have antiferromagnetically interacting Ising spins, and you put them on a triangular lattice, that's where the geometry enters, your third spin wouldn't know whether to be up or down. you might say it's frustrated and both options are equally unhappy or equally happy. So there's a degeneracy. Now you take this to a little richer setting, you get to the dimer model, where you can think of these sticks or dimers as a singlet. Then you can spin singlet, you can connect it back to physical systems. But often people also just think about these as dimers. And thinking about the fluctuation that it can be captured in a quantum mechanical sense, a fluctuation of these configurations that can be captured in quantum mechanical sense was this very influential paper, leading to be cited here at in Princeton. It's long been actively pursued that this sort of route can lead to rich physics from many configurations or not having a definite outcome that is not being ordered. You can have spin liquid ground states, and you can have anyons or fractionalization. So how would having degenerate ground state or many configuration possibilities lead to fractionalization? Well, you can start with this sort of, this is a allowed configuration of dimers. Dimers follow the rule that every site has to have one dimer touching, and dimers shouldn't collide with each other. So this is an example of a configuration that follows that rule on a triangular lattice. Now you can see that there isn't any kind of a pattern or regularity because this is a triangular lattice. Because there are many configurations that are legal, that follow the rule, but none of them are following a particular order. If you consider fractionalization here, you can think of these as broken singlet bond or removal of a dimer. Now, you can consider other arrangements that amount to movement of these fractional objects or monomers. Now, once you can move these monomers apart, or rather moving does not cost any additional energy, we say they are deconfined, and we can think of these monomers as fractionalized objects that are well defined on their own. So this is a way of getting fractionalization. Now you can see in coming to this possibility, the fact that your dimers are not rigidly ordered, unlike in this kind of columnar setting, is what allowed you to think about these monomers. Now these are sort of a set of pictures that some of you may be already familiar with, and this is a very canonical way of talking about geometric frustration. However, considerations of this geometric frustration up until now have been really limited to physics of spins. Now, spin is not a fundamental particle. You get spin out of electron when electrons cannot move. So that we can ask the question, well, if you focus on the spin aspect of electron, because electrons cannot move, you can, and then think of those electrons living on sort of a frustrated lattice, such as triangular lattice, and talk about this geometric frustration. Although there has been a lot of rich history of theoretical developments, seeing these physics to really pan out on a physical system is usually challenging unless you design a system. Really, only very recently, being able to really set up a very much designed setting on quantum simulators really allowed confident association of a physical system to this kind of physics. So now we can ask, is pursuing spin the only way? Is there another way to make use of this kind of geometric insight? What about charge? Now, electron is not something that you can grab on your hand, but our sort of intuitive picture is that of s orbital, kind of spherical object. So like, how do you get geometry out of that? That's where the trimer model of twisted bilayer graphene enters. So twisted bilayer graphene, this is actually experimentally obtained image of STM. But if you don't have STM in your basement and you want to think about what the twisted graphene should look like, you can take a slide and print out transparency, if you know what transparency is. Print out hexagonal lattice and twist them. And transparencies were a thing of like my youth. It kind of went out of fashion, but it's become fashionable again with moiré. I've seen my colleague Kim Phi Mac use transparencies to do the demo. Anyways, you can do the transparency, you can do it on PowerPoint. Invariably, what you will find is that when you take a hexagonal lattice and twist, you get this sort of pattern of well-aligned parts forming a triangular lattice. So in early days of twisted bilayer graphene, when the first experiments of reporting superconductivity was announced, everybody jumped on to say, okay, let me think about triangular lattice Hubbard model or something along that line. The problem is when you twist in momentum space, what you're doing is taking this original Brillouin zone and you have another Brillouin zone that you obtain by twisting, and you have this mini Brillouin zone, which came from a single valley. If you look at the band structure that you can obtain for the lowest lying band, you have this situation where different high symmetry points are behaving in a very different way. So this K point is degenerate. You can see there are two bands that are degenerate coming from two different valleys, but this gamma point will not be degenerate. You cannot get this kind of band structure out of a triangular lattice. So here is the conundrum. What you see with your own eyes looks very much triangular. So you really want to do triangular something. But this band structure tells you you cannot do that because you cannot get these high symmetry points to be, some are degenerate and some are not, for a triangular lattice. And this is actually much more reminiscent of hexagonal lattice. So how do you get a hexagonal lattice while having your electron weight or the probability density looking very triangular? And that is where this Vannier orbital show up. So if you are a young enough generation, or if you are a parent with young enough generation, you would know what fidget spinner is. This morning, I met someone who didn't know what fidget spinner is. But fidget spinners are looking like this, and you will see a picture shortly. Some people call this clover-shaped Vannier orbital or fidget spinner Vannier orbital. The point is, you have your electron weight spread out in 3 lobes, but the centers are going to be located according to hexagonal lattice. So you can make what you see with your eyes and the requirement out of the symmetry of the band structure happily all satisfied. So what does this mean to have an extended Vannier orbital? The Vannier orbital being extended means that there will be naturally extended range of interaction. This is an almost contact interaction. The centers are not overlapping, so it's not a traditional sense of contact interaction, but the lobes are overlapping. So this would be severely punished under repulsion as much as on-site is punished. However, if I think of sort of contact type interaction, this kind of arrangement where they're not touching or not overlapping should be okay. So the implications of having to think about this extended Vannier orbital meant that interaction would be necessarily longer ranged. And not only interaction, hopping will be also complicated. because hopping integrals are something that we figure out by considering overlap between the orbitals. So this observation of the binary orbitals came really shortly after the first birth of the twisted bilayer graph in physics. But then soon people started to kind of give up on it because it is really complicated and cumbersome to work with them. However, if you consider at 1/3 filling, this is what we've noticed in this paper. If you consider 1/3 filling, you have a nice situation where you can avoid any of this kind of touching or contact interaction and spread out these van orbitals. So without doing any calculations, I said I'm not going to make you do calculations after lunch. Without doing any calculations, you can already see that, okay, this is going to be some sort of an incompressible state. So what we started doing was to think about what would be the arrangement of these van orbitals. So here's a fidget spinner. This is what fidget spinner looks like. You can start with one orbital, and then you can start to tile the rest. So that's one way of tiling, but that's not the only way. Now, first of all, as you spread them out, you can see that this is an incompressible state because as you try to compress it, you will make them climb on top of each other or collide with each other. But another thing that you can notice is that there are multiple ways of spreading them out. Now, once you realize that there are multiple configurations, you have to ask how many configurations are possible. And that would have been normally a daunting task. The way we proceeded was Liang laid out a configuration and I laid out a configuration and they were different. And that's when we realized, oh, there are possibly many different ways. And I asked my student Kevin to go start trying to enumerate different ways of tiling. And he came back saying, you know, you won't be able to count this. There seem to be way too many. So there was a hint that there is something very rich going on. And it kind of made me really miss my late colleague, Chris Henley, because he is somebody who's made great contributions on geometric frustration. And also what I'm going to talk about tomorrow morning is very much leveraging his great contributions. But also, I was encouraged by kids willing to explore laying out of tiling, which happened around the same time. This was at Museum of Math. So we embarked on this journey of trying to figure out what will be the consequences of these orbitals being a geometric object. And what Kevin came back and said was that, look, Eun-Ah, there are way too many. You cannot count by hand. And then we realized, okay, then let's see what's been known about this sort of model. And turned out this trimer tiling is something that had been studied before by the StatMed community. And there is a Bethe-Ansatz solution which tells us that the entropy or the number of configurations is extensively many. The entropy is extensive. And one way to, although Bethe-Ansatz solution is not something that I want to impose on anybody to follow after lunch, but there are some simple geometric visual insights that one can gain to understand why there are many configurations and why is it extensive. So here we are starting with one configuration where none of the orbitals are touching, the triangles are arranged so that they're not touching. If I try to flip just one from here over, I will immediately run into touching the other orbital. But if I keep flipping, which we call the flip line, going across the entire system, I arrive at another legal configuration. So these flip lines would meet in a tri-junction. They can come together in a tri-junction or go out in a tri-junction, which means you have trivalent joining points of these flip lines. And what you can end up with is this kind of generalized hexagonal lattice. And these flip lines moving in and out is not going to cost energy. and that's called breeding entropy. So this is sort of a way to see why there are extensive degeneracy. I said earlier that having a degenerate set of large degenerate set of configuration can be a good setting to pursue fractionalization. And this told us that we should be thinking about fractionalization. But when I show these kind of pictures, people would often ask, Eun-Ah, please give me a Hamiltonian. Some people like to see pictures, but some people are much more comfortable looking at equations. Now, this notion of no touching condition can be compactly written in terms of cluster charging Hamiltonian. And there's a benefit to writing in terms of writing this Hamiltonian down, because once you write down this Hamiltonian, you realize that perhaps this is not restricted to the extended binary orbitals of twisted bilayer graphene, because one might be interested in pursuing different kind of physical setting. So what I'm showing here is that this no touching condition means if I have one side of this hexagon occupied, I don't want any of these gray parts to be occupied. And that means in this hexagon right here, I want only one side occupied. And also in this hexagon, I want only one side occupied. In this hexagon, I want only one side occupied. So that's what this term says. This cluster charging Hamiltonian says. It says, on these hexagons, I want there to be only one charge, and having more than one side occupied will cost me energy U. And taking U to be infinite will force me to be in a ground state. Writing in terms of equation like this help us see that how would we go beyond this setting, because nature does not like degeneracy. If we engineer ourselves into a setting where you are guaranteed to have extensive degeneracy, perturbations away from it would break that degeneracy. Now that we've written in terms of written down this cluster charging term, we can immediately see that interactions that's going beyond this, but the next leading term would be a fourth neighbor, the interaction between neighbors that are 4 lattice constants apart. So here, 1, 2, this is what we are writing as J4, U4. And this interaction term can have microscopic contributions from the Coulomb term and the Hund's coupling, which means this can have different signs. So now we have a phase diagram that we can consider. When U4 is negative, that extensive degeneracy will be broken down to this what we call brick wall phase. And when U4 is positive, this will be broken down to √3 by √3 phase. √3 by √3 in terms of, if I keep track of the centers of the binary orbital, it looks like a very familiar charge ordering pattern. Brick wall phase, if I keep track of the centers of the orbitals, it looks sort of like there is, this is an anisotropic phase. So there is 3-fold rotational symmetry is broken. So this is all nice and maybe even fun, but are there experiments to support these kind of ideas? The first experiment that got us thinking down this road was actually this experiment from MIT, where they're focusing on the fact that they are getting superconducting dome. But something that you can notice here is that there is a dip in the superconducting dome right here. So right after I saw this slide at a Zoom talk, this is published in 21. Zoom talk was earlier during COVID lockdowns. I asked Pablo, what is the filling? I was wondering whether it will be close to a third, because this was something that we've been thinking about. And turned out this filling is actually very close to a third. Next supporting evidence came from this paper where fractional churn insulator was, fractional anomalous Hall effect was reported. But here is incompressible state. where there is no slope as a function of magnetic field versus filling, which means this is an incompressible state with Chern number 0, and this is also occurring at a third filling. And this is our recent Nature Physics paper. These two experiments were done on magic angle twisted bilayer graphene, which has a lot of intriguing physics, but it also requires a great deal of care and control. Moreover, the heterogeneity in the twist angle can make it bring in complications in trying to make connection between experiment and theory. What we found is that these incompressible states that we are thinking about that is resulting from the extended nature of the binary orbitals are actually much more robust. They are not sensitive and fine-tuned to magic angle. So this is the transport data at angle 1.32, which is larger than magic angle. What we found, what rather Ginny and Mark found, is that when you go away from magic angle, a lot of physics that are very much tied to magic angle go away, and all that's remaining, that's giving this deep minima in conductivity, conductance, minima in conductance, are just the third fillings, minus 8/3, 4/3, 2/3, 8/3, so on. Now, the different curves here are measured at different temperatures. Now, this whole set of experiments gave us a rich set of experimental settings to think about. So this is at one angle of 1.32, and it's showing the transport gap of 140 Kelvin. This is very robust, nice insulating behavior. But now it's not just 1/3. So when I was laying out my fidget spinners, I was considering a simple 1/3 setting. But now I have different fillings, and we have this new challenge to think about how we can take all these real different numbers into account. The experiment was actually inspired by Dan's March meeting talk, which was really exciting. You know, when your student or postdoc, work hard preparing for the talk, and they give a talk, and then that leads to something that's always really rewarding, and that's the experience we had. But the data came with this different filling. We had the obligation to try to figure out what's going on. And the first thing that you realize is that when you have more electrons than just pure 1/3, of course, you cannot avoid some of the orbitals touching, but you can still try to think about configurations that will minimize the penalty of touching. And there are now more possibilities. This √3 by √3, which was one case for 1/3 filling, branches out to a whole set of different possibilities. Same is true with brick wall. When we looked at this difference between 8/3 and 4/3, what we noticed was that in-plane field dependence of the conductance was rather different. So for 8/3, in-plane field, especially minus 8/3, was just suppressing conductance. But for minus 4/3, it was initially enhancing conductance before it dies out. So this is a qualitatively very different behavior. Having this very sort of intuitive starting point helped us try to focus on how do we try to address these observations with the tools that we have at hand, which is pictures. So this is minus 8/3. Minus 8/3 can be thought of as adding 4 electrons per plaquette, starting from filling of -4, minus 12/3. To go to minus 4/3, I need to bring in 4 more electrons per plaquette, which means it is unavoidable to have double occupancies. So these magenta lobe fidget spinners have double occupancies. which means there will be spin physics between those two electrons. We can also look at what the Vannier orbital would look like for different values. And in zero in plane field, spin singlet with valley polarization is favored because that would you can choose a valley that will minimize the Coulomb cost. But at finite field, you would want to align spins. So when you align spins, due to be antisymmetric Pauli principle, you want valley to be anti-aligned. So this sort of just simple-minded kind of visual inspection already gave us a picture that can explain why once you start to have double occupancies, you might be able to have a crossover between two favored configurations. Initially at zero in plane field, you will start off favoring this valley polarized state. As you increase the in plane field, the Zeeman energy would start to favor the spin polarized valley anti-aligned state. On its way, you will be first closing the gap and enter another state. Turns out the amount of field that was necessary, around 10 Tesla, sort of works out with the ballpark numbers that we were getting. So it was very encouraging to see that not only the experiment confirmed the robustness of this incompressible states at 1/3 fillings, but some of the striking features could be even explained or rationalized from our starting points. So emboldened with these observations, now we're going to start thinking about what would it mean to have this geometric frustration of orbitals, and what kind of fractionalizations can we think about? Any questions at this point? No? Yes?
It's like the degeneracy is not protected in a way, right? So like how is it that it's so stable?
Did I say it's stable? Okay, I didn't say it's stable, but so so what you're seeing here are rich set of possibilities. Now, these two are not degenerate, which is why you can go from one to the other as you apply magnetic field in plane field. But that was actually, nevertheless, it was a good point that you're grabbing onto. So the question was, why would degeneracy be stable? So what happens with the degeneracy is at this U4 equal to 0 point, that's the only point where we have truly extensive degeneracy. Once you go to √3/√3 order, that is a, let's say, boring or charge order state. You only have threefold degeneracy depending on your registry. When you go to brick wall, you have a slightly more interesting setting where you have sub-extensive degeneracy. That is not as extensive as U4 equal to 0, but still nevertheless interesting. This whole starting point of cluster charging Hamiltonian, we keep learning as of yesterday. We keep learning that it's kind of a starting point to explore many different rich set of phenomena. This cluster charging Hamiltonian is not on-site interaction. It's a little richer. It's a little more complex. But it is not a full-blown Coulomb long-range interaction. So you can start from here and start bringing things in to see what kind of new things can you see. And it's not just immediate that you kill all rich physics and all degeneracy. And that's what I'm going to further explore, especially with the fractionalization. Any other questions? Okay, good, thank you. All right, so fractionalization. Actually, this was the next slide. Degeneracy gets lifted. Now, in the exactly solvable limit, which was solved by Bethe-Ansatz solution, there is the extensive degeneracy, but you go away from it with this U4 interaction. You either unicell triple or you enter a brick wall phase, and your extensive degeneracy is lost. Nevertheless, you can start think about fractionalization. So here is a way to think about fractional charge. If I have root 3 by root 3 with different alignments, registry, there are 6 different registries one can think of, depending on where the triangle is facing. And if those domains, 6 different domains meet at one point, this point actually you can prove has 1/3 charge, where when the charge is spread over the entire orbital, you can calculate the charge localized on this side by integrating the polarization density as defined. The difference that the fact that you have an order configuration means is that this fractional charge cannot move. So here, that fractional charge that I just showed you before, if I try to move it, it would require rearranging my orbitals, but I would immediately run into violation of no touching condition. So I am finding that once I'm in this order state, there is some issue with the mobility of my fractional charge. Here is another type of fractional charge setting, starting from root 3 by root 3 order state. Now here I have removed 1 electron. By rearranging my orbitals through flipping, I can move just 1/3 of charge away. So, and what it is leaving behind at its trail is a flip line. And this, if I look far enough away, also has 1/3 charge. And if I go to the brick wall state, which is the other side of the order phase, it has sub-extensive ground state degeneracy because along each line, I can change the direction of leaning. And this also means I can bound a fractional charge, 1/3 charge, at the domain wall between 2 different orientations of leaning. And in this case, because of the degeneracy, this fractional charge turned out to be actually deconfined. That is, the energy cost of moving it apart is not growing with the separation. But in the root 3 by root 3 state, the fractional charge that I was showing through the configuration was actually bound. That is, the energy cost grows with separation. So if this fractional charge cannot move, would it be still interesting? So tomorrow I want to talk about the exactly solvable point. I want to come back to the exactly solvable point where we found the monomers to have algebraic correlation. That is, they are not, the correlation function for the monomers to be apart follows a power law. But in these order phases, there is clearly a great deal of restriction on the mobility. Now, why would a fractional object that has difficulty moving be interesting? So before, I don't know, 2010-ish, when you find something that cannot move, you would have thrown it out. But nowadays, when you find things that have difficulty moving, and if it is some sort of fractional object, you start to think twice about it. And that's because of these notions of fracton. In this model, so-called X-cube model, which is a 3-dimensional model, exactly solvable model, these group of people found that you can have a setting where you have immobile particle that is completely immobile, that is a fracton. And sometimes you can have a fractionalized object that can only move along a line, although the model is defined in a 3-dimensional setting. So that was called line-on. Now, these models are, they are ingeniously engineered, which is really remarkable and interesting. But at the same time, because they are ingeniously theoretically engineered, you can imagine, especially this being 3D, you can imagine it being pretty hard to try to find it in a real system. Interestingly, Pretko and Razyovsky pointed out that there is sort of an interesting connection between the fracton physics and topological defects of a lattice. And you can think about there was observation that there's a connection between fractons and rank 2 gauge theory. So now we have a setting where we have sub-extensive ground state degeneracy in this brick wall phase. And this brick wall phase is something that you can get by starting with our cluster charging or no touching condition and introducing the next leading interaction. At least incompressible state has been observed. Are the insulating states that Jeannie and Mark or other colleagues have observed, is there evidence that they involve fractional charge? We don't have evidence that they involve fractional charge yet, but these are sort of promising initial observations that's encouraging us to keep thinking about what would be the nature of these fractional objects, fractional charge, monomers, and how will we detect them? How will we go after them? And it's particularly interesting because these kind of setting might be a way to go after this elusive fracton physics. So brick wall phase has line-on-like excitations because these fractional charge can move along the line, but it cannot move arbitrarily. And we are trying to figure out, is there a way to make contact between our observations and sort of a analytical theory understanding. This effort of trying to see what we started from just looking at pictures and start imagining how would you lay things down, and sort of the rich and well-developed understanding of geometry frustration has just started to kind of bear fruit until our this collaboration that I am just about to show you. Our observations were sort of like we laid things out, and this is what we find, and this is another thing that we find, and we've been sort of exploring and digging around to see whether there is a nice way to consistently capture what we are seeing. We started to look at started this project of trying to understand correlation between these fractional objects or the monomers, because Bethe-Ansatz solution at an exactly solvable point, because Bethe-Ansatz solution would give you the ground state degeneracy, but it is very, very difficult to study correlation functions from Bethe-Ansatz. But these are classical, we are still doing classical physics, which means at least we can try to do Monte Carlo. And that's what we started doing. Doing Monte Carlo simulation of classical Monte Carlo simulation is not necessarily straightforward and easy because of the degeneracy we have, which means in order to equilibrate, you have to explore the different states that you need to access. The different configurations in my degenerate manifold of states configurations are not accessed through local moves. The flip line that I showed you earlier is an example of a very long-ranged move you have to make in order to go from one configuration to another configuration. That means when you try to do Monte Carlo simulation, you need to have a global update in order to explore your different configurations. And that was pretty challenging. But Kevin is creative and resourceful, and with help of Roderick, we were able to actually explore this full phase space and get Monte Carlo results. And this is the phase diagram as a function of further range interaction, and the vertical axis is now temperature. So until now, when I was showing you phase diagram and talking about how the degeneracy, extended degeneracy of exactly solvable points gets lifted, I had just one axis, that is the further range interaction. Now with Monte Carlo, I can go to finite temperature. So the first thing that we noticed was that this extended degeneracy point, the exactly solvable point, does not stop at just being a point, but the behavior that you observe here kind of extends over to broader range of phase space once you go to finite temperature. Now, in units of U and taking this into the estimated value of the interaction strength, this gets us to tens of Kelvin. This is about tens of Kelvin. And that's, we're not talking about millikelvin. This is an accessible range of temperature. And what this phase diagram is telling us is that the cool physics of that extended degeneracy, if we understand what is there to study, should be accessible over a reasonable range at finite temperature and over a range of perturbation. So there is a sense to which it becomes more robust as you go to finite temperature, at least for a while. Another things that we were able to find was that in addition to the √3 by √3 pattern, I think this was the first pattern Liang wrote down, and the brick wall pattern that I wrote down, there is another order phase here that we named polar fluid. In the polar fluid phase, we break the invergence symmetry because only the triangles are all pointing in one way instead of having both ways. But the translational symmetry is restored. So this is the polar fluid phase, the new phase that we found by doing Monte Carlo simulation. And this is a √3 by √3 phase, and this is the brick wall phase. And here at the star is exactly solvable point. And in this phase diagram, we named it trimer liquid. When I use the word liquid, I mean that the monomers in this phase have power law correlations. So this is the power law correlation that you can see from the monomer correlation function that we calculated using Monte Carlo simulation. Having Monte Carlo simulation means not only that we can calculate these power law correlations, but we can also study the phase transition and study exponents to identify the universality class of the phase transitions. Now, this phase diagram that we were able to obtain by doing large-scale Monte Carlo simulation led us to something that we didn't know to expect. And that's the fact that this correlation, the power law correlations, there were not just one power law. Actually, there are two different power law exponents that we found. And what has been really exciting was that we can not only calculate these exponents with numerical simulation of Monte Carlo, but then we were able to leverage the analytical understanding and the framework of field theory associated with dimer models to actually calculate those exponents analytically and match with the computational results. But all of that will be the topic of tomorrow's talk. And with that, for now, let me summarize. Twisted bilayer graphene, TBG stands for twisted bilayer graphene. Even away from magic angle, is actually nicer because you can more readily do experiments. It's not as fine-tuned and finicky. Moreover, a lot of things that happen at twisted bilayer graphene that's mysterious and that we don't understand kind of goes away. And we can just focus on this very robust phenomena of 1/3 filling incompressible states. We believe the twisted bilayer graphene at 1/3 filling is a natural platform to think about implications of geometric frustration involving extended Wannier orbitals. This is a very new platform to think about geometric frustration. This framework leads to a novel route for fractionalization. Instead of starting from single particle physics, giving you your flat dispersion and letting interaction do the next job of turning that flat band at partial filling to your desired fractional turn insulator, we can start with extended degeneracy that we get from the interaction and ask what kinetic energy would do. Or maybe we can just stop even at the effect of interaction. And so there is a novel route to fractionalization. And one can now start asking questions like, can we somehow go between fractionalization associated with this cluster charging interaction and something like, or something that sort of involves electron moving around, that, such as fractional turn insulator. Finally, all this fun that we've had is not just thinking about the possibilities in vacuum, but it was really the inception of the idea came from looking at what's observed experimentally, and experimental evidences supporting robustness of the incompressible states at third filling is encouraging thinking about all this fun physics possibly occurring in 1/3 filling of twisted bilayer graphene. So tomorrow I want to talk about how we calculate this exponent and other exponents, and how we understand the critical phenomena associated with this transition or these other transitions, and what are the implications of this trimer liquid phase and how it relates to previously thought, previous ideas on different types of fractionalization, heavily relying on the literature and the established lore and theory of dimer models. But because we have a triangular object, the trimer instead of dimer, there will be a whole new spin on how things play out. So with that, thank you for your attention.
Floor is open for questions.
Yes.
So forgive me if I misunderstood, but I don't think you included like kinetic energy competition with the interaction anywhere.
Yeah.
Do you have any sense for like the scale of competition between the two? And like what's the leading order correction that you get once you include kinetic energy in this picture?
So if you have a flat band, what is the kinetic energy? 0, right? So there is my justification for first thinking about interaction effect. If I am really interested in very flat limit, my hopping and the scale of kinetic energy will be small. Small doesn't mean it's 0, but it is, I can justify starting from the effect of interaction and ask what would that mean. Now, when you start thinking about effect of hopping, now that I've kind of figured out what happens in the ultra strong interaction limit, you have to ask, can sort of the very classic way to think about hopping here will be sort of inspired by how you think about dimer models. So when you think about dimer models, the effect of quantum fluctuation is to ask, can you do local flipping moves to connect to another state that is in your degenerate manifold? So we asked, by flipping our orbitals, which would amount to hopping, right? If I flip from here to there, the center moved. So that's the effect of hopping. We can ask, how many hoppings do I have to go through to get back to a configuration that is legally allowed? And so those are the kind of things that we've thought about, which I will discuss more tomorrow. So I have not discussed the effect of hopping today. So you were not missing anything, but we'll talk about that tomorrow. Long story short, it is pretty complex and we haven't solved it yet all. We've made some progress in various different angles, but we're far from having solved it. It's a very rich and complex problem. But while exploring to try to ask questions, like very logical question, right? That's a very logical question. While trying to ask these kind of very logical questions, we've kind of ran into very many different ways that this cluster charging model can be the starting point of very interesting and diverse scenarios, which I will discuss tomorrow. Yes, yes.
Okay, yeah, maybe you'll talk about it more tomorrow, but I'm just curious about the order parameters you listed in the your QMC analysis, like P and S.
Yeah.
So how can I understand
Different order parameters here? Yeah. So what is S? Yes, S has to do with, so this root 3 by root 3 state. So this is a charge order state. So S would be the Fourier component of density associated with the ordering wave vector. So you can see here, this is, if I just look at the centers of the orbitals, it's a tripling of the unit cell. So my lattice translational symmetry has now been reduced to lattice translation of the tripled unit cell. And that means there is a particular component of the Fourier transform of density. So that would be like structure factor with the right Q. So that's what S is. P here is about the polarization. It's very trivial, but it's also interesting. Triangle is not supersymmetric. So when you flip, you can define polarization with a triangle. Yeah. So because it's a triangle, you can define polarization, and this P being non-zero means everybody's pointing in the same way. So polar fluid has polarization, so everybody is still yellow pointing the same way, but translational symmetry has been restored. So here, everybody is rigidly in the triple unit cell. In the polar fluid, they're kind of moving around. Polar fluid is a little bit like nematic, if you know what electronic nematic is, where you have nematic, it means you have reduced rotational symmetry from whatever you started with to lower one, and but you still have translational symmetry. We called it polar fluid because nematic should have a headless vector as an order parameter. Here, clearly, there is orientation. But it is also like Z2. So that's what polar fluid means. And this is a disorder state, thermal disorder state, where none of the order parameters are finite. Yes?
So the polar fluid does not have ground state degeneracy.
Polar fluid does not have ground state degeneracy. It would have, there's a degeneracy of twofold, right? Up or down. And to be in a polar fluid means that that symmetry is spontaneously broken, right? Like in the Ising ferromagnetic sense. In root 3 by root 3, there is that up or down that's broken, and also the registry of threefold tripling of the unit cell. When you have a charge order on a lattice, and if you have a reference point, you can define phase of charge order based on the registry. So there are threefold degeneracy in the ground state. And a ground state will be choosing one out of those three possibilities and choosing one out of up and down polarization. Yeah, but all the cool extensive degeneracy physics is right here and in this trimer liquid region. And brick wall state still has sub-extensive degeneracy. So in the 2D system, brick wall phases degeneracy goes linear to the linear dimension, not L squared.
Is that phase boundary first or second order? The green one.
Great question. So some of the phase boundaries are second order, some are first order, some are kind of hard to tell because down here it's kind of glassy. But I'll show more of this tomorrow, because in order to say I know what the order of the phase transition is, I should show the evidence through scaling and so on. So we'll go over that tomorrow.
If it was first order, like that would be kind of true, right? Because you could melt away degeneracy, I guess, right? If you have still sub-extensive scaling.
Repeat that?
Like, I mean, if it's first order, like if I have like a block of ice and I just like put heat into it and my ice gets smaller or something, if you still have like a scaling with the degeneracy, like with the system size of the degeneracy.
Yeah, but I think that's also why it's kind of hard to nail down the order of transition here. It seems first order to the best of our abilities, but yeah, out here it seems kind of first order, but it also is kind of glassy because you can form these domains. I mean, you know, that's what makes it hard to do simulations. Yes?
Even though like these layers have a discrete rotational symmetry, can we have an analogy to vortices and PKTs? Like, understand these like
Yeah.
the transition between trimer liquid to square root. In still theory level, maybe we can force grain into like continuous.
That's what we'll do tomorrow. Yeah. Don't have heavy breakfast because you don't want to be sleepy. Any other questions?
Okay, if there's no more questions, let's thank the speaker.